Okay, so this is a staggered conformation, just in case you're not familiar with that. And what it means is, when we look down this, there's 6 bonds. We go front, we go a bond off the front atom, back, front, back, front, back. Okay? In an eclipsed conformation, so I'm not going to show those right now. The 3 most stable conformations for a carbon-carbon bond are going to be staggered. The eclipsed conformations would be like rotate 60 degrees, and the ethyl group would be right in front of the H, the bromine would be right in front of the C6, and the H would be right in front of the isopropyl. The bonds would eclipse one another. Those are the least stable conformations. Okay, there's going to be 3 eclipsed conformations. Those are the least stable, highest energy conformations. There are 3 staggered conformations. Those are the most stable. So let's do that. I'm going to hold what am I going to hold? I'm going to hold the back carbon the same, and I'm going to rotate the front carbon. There's no rhyme or reason to how to do this, okay? The molecule itself can rotate clockwise or counterclockwise, and in fact it will do both. Right? This whole molecule is tumbling through solution or through the air. If, initially it's tumbling in such a way that as we see it, the front carbon is going clockwise. Bang, it runs into the flask wall, it runs into a solvent molecule, it runs into the tail of itself, and all of a sudden that bond starts spinning the other way. All right, so these molecules, it's not like they have a set way to move. Yep.
If there was a double bond between 8 and 7, would you still be able to rotate it?
No. That's a good question. So, like between C2 and C3, you can draw, let's do that. C2 and C3, if I were to look here, so C2 is the front, methyl H, and then off the back carbon, we have the rest of the molecule and H, right? And again, I've canted that just enough you can see it. But now that's a pi bond, okay? And so the way the orbitals work on that, the sigma bond is cylindrical between the 2 atoms. The pi bond is bonding above and below, so it hooks in 2 places, and that's going to hold it rigid. This is the only conformation of the double bond. It doesn't move at all. This one does. So, like I said, let's move. I'm going to hold the back carbon the same. I'm going to rotate the front carbon clockwise. That equilibrium arrow, 2 different arrows, one going left, one going right, says these 2 structures turn into each other. Keep leaving my eraser in the wrong place. All right, I said I was going to leave the back carbon alone. Make sure you do that. If you start rotating both of them, there's nothing wrong with rotating both of them. It's just it's one more thing you got to keep track of, and it's pretty easy to screw that up. I'm going to go 120 degrees. So I'm going to bring the ethyl down here, the bromine over here, and the H up. It's going to be staggered, so there you go. Ethyl, bromine, H. Right? And now the next one is just another 120 degrees. So bromine goes to the top. Ethyl comes to the left. H goes down. And now if I do 120 degrees more, ethyl goes to the top, bromine to the right, H over here, and I'm back to where I started. 320 degree rotations is 360 degrees, a circle. Yep.
Do you have to rotate the front ones or can you rotate the back ones?
No, yeah, absolutely. I could have said I'm going to hold the front the same and I'll rotate the back ones. I could have rotated counterclockwise. Either of them. Right? So, like, you can almost think about it as yourself. Like imagine I could take this whole thing and rotate the entire structure, not back and front relative to each. I could just look at it like I'm upside down. The same. All right. If you do anything, if you redraw or you relook at or you reimagine a molecule from a different perspective without any bond rotation or bond changes, those are superimposable structures, all right? You can always treat the molecule as if it's a thing, because, it is. And I can pick it up, I can turn it around, I can flip it over. Obviously now, one single molecule is way too small for that. Like, we cannot do that. We've gotten to where, in the last few years, we can implant a molecule on a surface and we can get a picture of it. Like an actual image of it. But everything has to go right for that to happen. We can't like tumble it around and get a picture of it. Okay, so these are the 3 staggered conformations of the molecule. All right, and you're going to see in the textbook, you're going to see me talking about it, these energy diagrams where we have energy on the y-axis and some constant about the molecule on the x-axis. The thing on the x-axis can be a bond angle, it can be a bond length, and we plot energy against it. It's a way to plot stability versus some feature of the molecule. I'll define dihedral angle here in a minute, see if it's on the screen. That's on the screen. Cool. All right. So as we go here, the staggered conformations are these low energy conformations. The eclipse conformations are at the high points. This is not quantum mechanics here, all right? Bond rotation is not quantized. It's just like an axial. So the dihedral angle doesn't have to be 0 or 60 or 120. It could be, 5.87 or 5.871 or 5.872. It freely rotates. For our minds, it helps to think about what is the most stable and what is the least stable. And then just interpolate. The other thing is, this tells you about time. It's not direct, you have to infer it. But the molecule is going to spend more time low here, where it's more stable. Low energy is more stable, high energy is less stable. So it's not like a smoothly running axle. Right? If you're driving down the road at 60 miles an hour, your tire is turning uniformly. If it's a smooth ride, it's almost a perfectly uniform turn. This is a much more rugged ride. That bond's spinning, it spins down here to a low energy point, and it slows down. It hangs out down here. It may even bounce back and forth a little bit. And then when it does this, it's like a roller coaster. Whoop! The molecule is going to spend very, very little time up here. This is important just to think about in terms of the molecule itself. It also becomes important when we start thinking about chemical reactions. Let's say you have a molecule that can only react when it's in this conformation, the eclipse conformation. If that's the case, that means that molecule is not going to react very well, right? Because you may have heard, if you haven't, we'll go through it, reaction rates tend to increase with increasing concentration. Effectively, the concentration of that eclipse conformation is really low. So I'm talking about time here, right? If I look at one molecule, if I put a little tiny GoPro on a molecule, I'm going to see it down here a lot. I'm hardly ever going to see it up here. If I look at a population of molecules, if I say look at a million molecules, 999,990 will be here. 9 of the others will be somewhere in between, and maybe 1 is going to be in the eclipse conformation. Yes?
Would heating up the mixture cause more molecules in the eclipse?
No, not exactly, though I know what you're getting at. If you heat so again, like energy is temperature is energy. So if we heat this up, the proportion of time spent in the two, staggered versus eclipse doesn't change. But the rate of going from one staggered to the other, and that is through here, increases. So an individual molecule passes through there more often. Okay. So, which of these 3 staggered First question is there a difference in the stability of the 3 staggered conformations? All right, everybody says there is. Which of the 3, take 30, 40 seconds and think about it, which of the 3 is most stable? Should write down. I'll put letters with it. You should write down which of the 3 staggered conformations you think is most stable. You don't have to tell me. You don't have to tell your neighbors, but you'll want to check yourself. Like I say a lot in this class. Or a lot when I deal with students, a lot of what you're doing here in college is learning how to be honest with yourself about what you know and what you don't know, and how to improve that. Right? There is nothing wrong with not knowing stuff or being wrong about a question. As you guys work problems, you're going to get a lot of them wrong. Be brutally honest with yourself if you actually understand it. Because a lot of times what will happen is students will come and tell me, I worked all these problems and I didn't quite get it, but I looked at the key and I understood it. And that is a big step on the pathway to being able to successfully work a problem, is to have the answer make sense to you. But it's not, I'm not going to give you a test and say, here are the answers, do they make sense to you? I'm going to ask you to give me the answer. And so that's one more step. Push through that. And you're doing that in all your classes. It's not just this class, right? And it is really hard to honestly assess your skill. Some of you out there, I'm going to come back to this in a minute. I like pop psychology a lot more. So some of you out there are cocky. And you'll always be like, oh yeah, I got this. Even when you don't. And those of you who are like that is how I was. And I shouldn't say how I was. I think I've gotten a little bit better at it, but if you ask my wife, I'm still like that most of the time. All right? So, do you tend to think you're right? And if you do, just know that about yourself. There's nothing, it doesn't make you a jerk, it doesn't make you a bad person. Just know it about yourself. And always sort of be like, I need to maybe check myself. Some of you don't have that confidence and always think you're wrong. That is my wife. Right? And so I can win. I'm loud, I'm bigger than her, and I'll just be like, yeah, the answer is this. We do this. And then 2 years later, we're broke. So if you are that person who's not quite as confident in your answers, again, that's not a bad place to be. That's probably an easier thing to recover from. But have some confidence. You've gotten here, you probably know what to do. All right. So A, B, or C, circle one of them, tell yourself that's what you think is most stable. And then I'll go through the answer here. So there's a couple of things to define here. So in A, the ethyl and the C6 are anti. So anti means the thing on the front is directly opposite on the projection, the thing on the back. That is an anti-relationship. The other relationship we have is a gauche relationship. C6H11 is gauche to bromine. The isopropyl is gauche to the ethyl in A. In every Newman projection looking down a carbon-carbon single bond, there will be 6. 1, 2, 3, 4, 5, 6. There will be 6 gauche interactions. We would like to minimize how many of those do not involve hydrogen. Okay? So, in A, I've drawn the only 2 non-hydrogen gauche interactions. C6H11 and bromine, ethyl and isopropyl and ethyl. In B, I'm just going to write G's here. In structure B, we have 3 non-hydrogen gauche interactions. And in structure C, we again have 3. So A is going to be our most stable staggered conformation. A also has the advantage that, if you look at, this is something else you can look at as a tiebreaker. You want to have the 2 biggest groups anti to each other. So the biggest group on the front carbon and the biggest group on the back carbon should be anti. If you have the same number of non-H gauche interactions. And then, so if we look at B and C, the big group on the front carbon is ethyl. Why do I say ethyl is bigger than bromine?
More C's.
It's got a larger volume. So really what we're looking at here is volume, not mass. An ethyl group weighs less than a bromine. But a bromine's just 1 atom. Doesn't take up that much space. An ethyl group, especially if you think about it swinging around, remember, the ethyl can rotate around this bond, it can rotate around that bond. Like, it takes up a lot of space. If you saw the last class, I like to use the analogy of, you're flying, and you're in an aisle seat, somebody's going to be in the middle seat. You'd probably rather have, like, a normal-sized human who goes straight to sleep in the middle seat next to you than a 6-year-old who's just, like, all over the place. Right? So that bromine just sits there. Takes up whatever space it takes, but that's it. The ethyl swings around wildly. As you go to B and C both have 3 gauche interactions that are non-H. And as you start judging those, you can judge the interaction. And this gets pretty qualitative. But as I look at this, again, bromine is going to be smaller than ethyl. So B has the bromine between the 2 big groups on the back carbon. So B is going to be a little bit more stable than C, which has the big group on the front between the 2 biggest groups on the back. All right, so you're just trying to minimize gauche interactions. And again, I can't emphasize this enough. The 3 staggered conformations are lower in energy always than the eclipse conformations. Okay, so practice those, draw molecules, look at molecules in the book on Wiley Plus. and look at Newman projections from that. I'm going to erase this. Let me give you a minute to daydream. Think about a question or two. Anybody? All right. Hit pause at home and stretch your legs. You come back. All right, the last bit of class today, I want to talk about cycloalkanes. Black bites the dust. That molecule is called cyclopropane. What's the hybridization of those three carbons? sp3, yeah. 4 things on them. What's the bond angle of the carbon-carbon bond?
One of them, I don't know.
Yeah, no, it's good. No, cyclopropane's a pain in the ass because of the confusion that was just evidenced here. I don't know if you guys can hear. I don't know if the microphone picks up the class. That's tetrahedral. The bond angle ought to be 109.5. That's an equilateral triangle. What's the angle inside? 60.
I have a question. How is it SP3? I don't know if I'm missing something.
I don't either. So there's 4 things on that carbon. All right? There's 4 different groups attached to a carbon. It's sp3 hybridized. I may have mentioned, I oversell this. So let me say, first of all, what you need to be able to do. You absolutely need to be able to look at a molecule and tell me what the hybridization of a carbon is. And also, hybridization is a bit of a fudge, right? Hybridization is a way to sort of approximate molecular orbital theory. Cyclopropane is a molecule that really, it kind of blows up. Because by hybridization, we would really like to have a 109.5 degree bond angle there. As you say, in an equilateral triangle, that angle is 60. Question?
I'm still a little confused. So if you look at carbon 3 on the left molecule, it's sp2.
Yep.
But it still has hydrogens attached to it. So why would the...
It's only got 3 things, though. Okay, so carbon 3 is bonded to carbon 4, a hydrogen, and carbon 2. It's got 4 bonds, but it's only attached to 3 different things.
I don't know why I wasn't like processing that.
No, that's why we're here. I'm smiling. You can't see that. I just look like a cartoon villain waving my hand. This guy puts a mask on and starts talking about exam 1. It's really frightening. So, hybridization is how many different things are attached to a carbon. Or if you like, what kind of bonds. So if you see a carbon involved in 1 double bond, it's sp2. It's got 2 double bonds or a triple bond, it's sp. If it doesn't have a multiple bond, it's sp3. So like I said, this would like to be 109.5, and yet it's 60. The result of that is the orbitals actually deform a little bit, and the bonds aren't as strong. So in the case of cyclopropane, the sigma bond is not directly between the 2 carbons. It's kind of outside. All right? It's like it's at a crowded party and it's kind of a handshake around somebody who won't get out of your way. You remember crowded parties, right? Okay. So there's angle strain associated with cyclopropane. That angle strain is just saying there's strain put on the bonds because the desired atomic geometry can't be there because of geometry. Right? Equilateral triangle has an angle of 60 degrees internally. There's less angle strain in a cyclobutane. There's still a little, actually 5 and 6 membered rings tend to be really pretty stable. So let's jump ahead to that. I'm going to jump ahead to cyclohexane, which we're going to spend, the rest of chapter 4 is going to be dealing with cyclohexane. It's a representative ring that kind of fit all the others. But cyclohexanes also are the most stable all single bond rings. That ring looks planar, but that ring is not planar, and that's what we're going to be looking at. All right, so if you had benzene, so in blue is cyclohexane. That's a terrible drawing. The purple molecule is benzene. All 6 of the carbons are sp2 hybridized. That means they're trigonal planar. Benzene really is planar. The bonds are, the bond order between any 2 carbons is a bond and a half. So they're shorter bonds. Benzene's smaller. So benzene's flat, a little bit smaller. These are 2 different compounds. Benzene is a different molecule than cyclohexane. Okay. Cyclohexane is not flat. Cyclohexane exists, if you've read ahead or looked at the PowerPoints or talked to older friends who've had organic chemistry, cyclohexane exists in there are 2 chair cyclohexane conformations for every cyclohexane molecule. That could have been said better. Every cyclohexane molecule predominantly exists in 2 conformations that we call chairs. Let's just jump into that. So if I look at this, if I look at cyclohexane from the side, I'm going to label the bonds A and B. Those bonds are parallel to each other. And the way we're going to draw this, right, if I look at cyclohexane exactly from the side, bond A is directly in front of bond B. Just like in the Newman projections, that doesn't work, right? So we cant the molecule. Let's say we're looking exactly edge on at the cyclohexane. A is directly in front of B. Purple and blue, right? Bond A is directly in front of bond B. We can't see anything, so we cant it like that. The front bond, bond A, is lower on the board than B. And then 1 carbon, right? Bond A and bond B both bond to 1 carbon, and that is going to be up. And bond B and bond A bond to another carbon, and that one will be down. That's the chair. My chairs aren't all that great. Some of you will draw better chairs. It's not a chair like you're sitting in. It's more like a chase lounge. Right? So picture a person sunning themselves on a chase lounge. You will also see chairs on Budweiser cans. And once you get immersed enough in organic chemistry, you will see the chair shape everywhere. All right? Yeah.
The board kind of draw like a different chair. They're like the winding constant. It's like
I don't care how you draw it. I care that you get basically this shape. Right? A and B are parallel. A is in front of the board. B is behind the board. The plane of the board goes right through here.